Welcome back to the deep dive. Today we're looking at a pretty wild cosmic news. It's about an object that's really got astronomers talking, maybe even scratching their heads a bit. We're going deep into the sources on ASKAP J1832-0911. An international team found this thing, and it's blinking, bizarrely. Our mission today, to unpack why this object is pushing back against our standard models of how stars evolve and die, and why some are whispering about new physics.
Yeah, it's a fascinating one.
Yeah.
And the first thing you need to get is that ASKAP J1832-0911, it belongs to this category that's only really just been recognized. They call them long-period radio transients, or LPTs for short.
LPTs. Okay, so that's different from pulsars, right? I mean, we know pulsars blink really fast.
Exactly. Pulsars, they flash maybe multiple times a second, super quick. LPTs, though, their radio pulses are much slower. We're talking minutes, sometimes even hours, between pulses. They're the slow blinkers of the cosmos, you could say.
And you said this is a new category, so we haven't known about these for long.
Not at all. It's really cutting-edge stuff. The first ones were only flagged globally, I think, back in 2022. And as of now, there are maybe only 10 known LPTs in total, so it's a very small group.
Wow. Okay. An exclusive club.
It is. And this particular object, ASKAP J1832-0911, it's like the VIP member who breaks all the club rules. It does the slow blinking thing, yes, but it adds this huge twist. It pulses in two completely different kinds of energy simultaneously. You get low-energy radio waves, and at the exact same time, you get high-energy X-rays. That's a first. The only LPT we've ever seen in X-ray.
Synchronized radio and X-rays. Okay, let's get into the rhythm of this thing. The timing is key here, isn't it? What's the actual pattern they observe?
Well, the pattern is almost unnervingly regular. When it pulses, the pulse itself lasts for about 2 minutes. During those 2 minutes, it's bright, really bright in both radio and X-rays. Together,
2 minutes on. Then what?
that it repeats perfectly every 44 minutes, like clockwork.
44 minutes?
Yeah.
It's like oddly specific and very long compared to a pulsar. If we're thinking this is some kind of spinning dead star, like a cosmic lighthouse beam sweeping past us, does that slow 44-minute period tell us anything? Does it mean it's old?
That's exactly the implication,
Yeah.
If it is a dead star remnant, which seems likely, either a neutron star or maybe a white dwarf, we'll get into that 44-minute spin, it suggests it spun down a lot over its lifetime. There's this process, rotational braking, where the star's own magnetic field typically slows it down. Getting down to a 44-minute rotation suggests it ought to be really, really old, maybe 500,000 years, perhaps even more.
So it should be like a quiet, fading ember.
Yeah.
Geriatric, almost.
That's what the standard models would predict. It should be quiet, winding down, not this, active, energetic beacon flashing across different energy types.
Excellent.
So that's the first big puzzle. It spins slow like an all-star, but it shines bright like a young one. And just to place it for you, it's inside our own galaxy, the Milky Way, about 15,000 light years from us, over in the direction of the constellation Scutum.
Okay, 15,000 light years. Still in our neighborhood, cosmically speaking.
Relatively, yes.
Yeah.
And just to hammer home how weird that 44-minute cycle is, pulsars, the ones we're familiar with, they spin in milliseconds to maybe a few seconds, thousands of times faster.
Yeah.
This 44-minute regularity is it's way out there. It pushes the boundaries of what we thought these kinds of objects could do.
So the slow period is strange, the brightness is strange for that period, but the dual energy, the radio and X-ray flashing together, that seems like the really unique part.
It absolutely is.
And that brings us to how they even found both signals. The story there sounds like pure unbelievable luck, cosmic coincidence.
Oh, it really was. So the first detection came from the ASKAP radio telescope array. That's in Australia. ASKAP has this huge field of view. It surveys enormous patches of the sky looking for radio signals.
Okay, so ASKAP spots the radio pulse. Makes sense.
But here's the kicker. At the exact same time ASKAP was seeing that radio flash, NASA's Chandra X-ray Observatory happened to be pointed at the exact same tiny little spot in the sky, and Chandra wasn't even looking for this thing. It was observing something else entirely.
No way. That's incredible. So if Chandra hadn't been looking right there, right then...
We'd only have the radio data. We wouldn't know about the X-rays, and the puzzle would look completely different. We might not have even realized how truly odd this object is.
That timing is just mind-boggling.
Yeah, the researchers themselves called it finding a needle in a haystack. Think about it. ASKAP sees this wide area. Chandra sees this tiny pinpoint within it. For a 2-minute pulse, happening only once every 44 minutes, to occur precisely when both telescopes were looking at the same spot. It's sheer serendipity. They didn't even realize they had the dual detection until later when they compared the logs.
But what incredible luck! And it suggests something important, doesn't it? Finding one like this, even by chance.
It hints there could be many more out there.
Right. We just weren't looking the right way, or maybe didn't have the tools lined up before. This dual observation, it's like it gives us a new template. Look for the slow radio pulse, then check for the X-rays.
Exactly. And that template leads us right into the physics problem. Because why is finding both radio and X-rays together such a big deal? Why is that the crucial clue here?
Okay, let's break that down. Radio waves and X-rays. They're very different beasts, energy-wise.
Massively different. Radio waves are very low energy, like the lowest energy form of light we generally detect from space. X-rays are way up the scale, super high energy, just below gamma rays. We're talking opposite ends of the electromagnetic spectrum, really.
So it's not just blinking. It's blinking in, like, infrared and ultraviolet at the same time, but way more extreme. Low radio hum and a high-energy X-ray blast generated by the same event in that same 2-minute window.
Precisely. Imagine trying to build something that when you flip a switch, it simultaneously produces, I don't know, the gentle warmth of a tiny light bulb and the roar of a jet engine. Any explanation, any theory you come up with for ASKAP J1832-0911 has to explain how it generates both these extreme energy outputs together. That really tightens the screws on the possible physics involved. And current models, they really struggle with that.
Okay, so the 44-minute clock is weird, the dual energy is weirder, and then it gets even stranger because the sources say this thing isn't even consistent over the long term. There's variability over months.
Yeah, this is maybe the most baffling part. It has this perfect short-term clock, the 44-minute cycle, but then it also seems to have this long-term light switch. When they first caught it back in February 2024, it was incredibly bright. Both radio and X-rays were just blazing.
Like the on state.
Exactly, but then just 6 months later, they looked again, follow-up observations, and the radio signal, it was 1,000 times fainter, practically gone. And the X-rays, completely undetectable, nothing.
It just switched off.
Or dimmed dramatically. It basically went dark, yeah. It seemed it kept the 44-minute beat. A little radio signal was left, still followed the pattern, but the overall power output just plummeted. So you have this combination. A super rigid, short-term pulse, coupled with this massive on-off change over months. Astronomers are saying that specific combination is unlike anything else they've ever cataloged in the Milky Way.
Wow. Okay. So that dramatic shift from blazing bright to almost silent, that really throws a wrench into figuring out what this thing actually is. This is the identity crisis you mentioned.
That's it, exactly. Because if it can just turn off its main energy source like that, what kind of object behaves that way? This is where we start bumping up against the limits of current astrophysics. To really get why this points towards new physics, you have to understand a core assumption it seems to be breaking.
Okay, what's the rule it's breaking?
Well, for the dead stars we thought we understood well, like pulsars and magnetars, there's supposed to be a pretty tight link between how fast they spin, how strong their magnetic field is, and how bright they are, how much energy they radiate. Generally, as they spin down over millions of years, their magnetic fields weaken and their energy output drops off predictably. It's called the spin-down luminosity relationship. ASKAP J1832-0911 is just way off that chart. It's thousands of times brighter than it should be for something spinning as slowly as every 44 minutes.
It's too slow to be that bright, or too bright to be that slow.
You got it. The star clearly didn't read the physics textbook on how it's supposed to fade away gracefully. And that forces us into considering the main hypotheses, even though, frankly, both of them have serious problems with the data we have.
All right, what are the leading contenders? What kind of dead star could this be?
Okay, so hypothesis 1. It's an old magnetar. A magnetar is a type of neutron star that's the superdense core left after a massive star explodes. Magnetars have the most powerful magnetic fields known in the universe. Insanely strong.
Okay, powerful magnetic field sounds promising for generating energy.
It does. But the problem is, like we said, a magnetar spinning this slowly should be ancient, maybe 500,000 years old or more, and by that age, it should be pretty much inactive magnetically speaking. So if it is a magnetar, its magnetic field must be doing something totally unexpected, generating all this energy in a way we've never seen or predicted for such an old, slow rotator.
So the magnetar theory needs some kind of unknown energy mechanism for old objects. What's the alternative?
The second main idea is that it could be a highly magnetized white dwarf. A white dwarf is what's left after a star like our sun dies, much less massive and less dense than a neutron star.
Wait, hang on. One theory is a neutron star, the core of a giant star. The other is a white dwarf, the remnant of a sun-like star. Those are fundamentally different kinds of objects, aren't they, in terms of mass and density?
Hugely different. That shows you how uncertain things are. We're basically trying to decide if this thing has, say, the mass of our sun squeezed into something the size of the Earth, that's the white dwarf picture, or if it has more mass than our sun squeezed into something the size of a city, that's the neutron star picture. The fact that both are on the table tells you we're really grasping at straws based on current models.
Okay, so what's the problem with the white dwarf idea?
Well, white dwarfs can have strong magnetic fields, but to generate this specific kind of synchronized radio and X-ray emission with this much power, this white dwarf would need an extraordinarily powerful magnetic field, possibly the strongest magnetic field ever inferred for any white dwarf in our entire galaxy. It would be pushing the absolute limits of what we think white dwarfs are capable of physically, maybe even beyond those limits.
So it sounds like no matter which path you take, magnetar or white dwarf, you have to invent some new physics or stretch the existing physics to an extreme degree.
That's the situation, yes. The researchers involved are very clear about this. They state quite plainly that current theories do not fully explain what we are observing. It's just baffling.
And that's the bottom line, really. This single object is forcing a rethink.
It really is. It makes astronomers reconsider some fundamental ideas about how dead stars work, how they generate energy, how their magnetic fields behave over incredibly long timescales. It strongly suggests there's some physical mechanism out there maybe related to how magnetic fields interact or decay in very old, slow-spinning stars that we just haven't accounted for yet. It really could be opening a door to new models of stellar evolution.
Okay, so let's try and synthesize this. What's the big takeaway here? ASKAP J1832-0911, this weird blinking object, it's acting like a bridge, isn't it? A bridge between things we used to study separately, these radio transients and X-ray transients. It's showing they can be linked, maybe even manifestations of the same underlying objects.
That's a great way to put it. Connects those dots. And the exciting part is now that we've seen one, we know what to look for. The belief is that these objects might actually be quite common, we just missed them before. And because they're apparently extremely bright in radio waves when they're in their on state,
We should be able to find more now.
that's the hope, especially with better instruments. We need that dual detection capability. For instance, there's a proposed new X-ray telescope called AXIS, the Advanced X-ray Imaging Satellite. If it gets built, it would be something like 10 times more sensitive than Chandra was when it launched. With tools like that, combined with next-generation radio telescopes, the prediction is, well, by the end of this decade, we could find dozens, maybe even hundreds of
Yeah.
these LPTs.
Wow, so a whole new population of cosmic objects waiting to be discovered.
Potentially, yes. A whole new window onto the late stages of stellar evolution.
So here's the final thought for you listening out there. We now know the universe contains these, well, stars or stellar remnants, whatever they turn out to be, that can keep a perfect 44-minute rhythm pulsing across both low-energy radio and high-energy X-rays, like a perfectly synchronized multi-frequency clock, only to then, months later, dramatically dim or switch off, completely defying our current understanding of how these dying stars are supposed to lose energy. Given that this behavior is unexplained, that it challenges these basic assumptions, what fundamental rule about how dead stars generate power, about their magnetic fields, about their rotation, what rule will ASKAP J1832-0911 force astronomers to throw out next? That seems to be the big question driving the next wave of discovery.